Hello, everybody, dear members of the audience, online audience, and on-site audience in front of me. I'm Professor Buzdugan from the Technical University of Cluj-Napoca, Romania, and I have the honor to chair this plenary section of the conference. This plenary session is entitled Continuous Waveform Capture from Proactive Power Quality Monitoring Analysis. And it will be presented by two significant scientists in this field, Mr. Bill Howe and Mr. Thomas A. Cook. Mr. Bill Howe, it's a project manager at the Electric Power Research Institute, in the program manager for power quality research. In the domain of power delivery and utilization sector. Mr. Howe's is a primary, Mr. Howe's primary areas of expertise are power quality, research information, knowledge development, and so on. He being a very prominent scientific in this domain. Also, beside him is Mr. Thomas Cook, Tom, so-called, manages project set B, power quality data and monitoring for the same institute. His primary focus is working with utilities and industry experts to identify and develop research for power quality and power monitoring industry. I guess we have a very, very interesting and exciting plenary session. I give the floor to the presenters. I don't know the order. Mr. Bill Howe and Mr. Thomas Cook, the floor is yours.
Thank you very much. And I just want to make sure that from the start here, if you can see my screen, I've shared my screen, if I could get confirmation that you could see that.
Yes.
Okay, thank you very much. And thanks for the introduction. Bill Howe won't be with us today. It was between he and I and doing this work, and he was going to, is either going to be himself or myself present on this. We had a conflict with IEEE, and so we're working together to present at both of those actually this morning. So I'll be presenting for this session. And again, we're looking at continuous waveform capture for proactive PQ monitoring analysis. With this presentation, we'll be looking at some of the backgrounds on why we are doing this work, and looking at some of the PQ monitoring today, and just giving a brief background on that, and why we're looking to move forward into a more continuous waveform monitoring method, and some of the struggles that go along with that in the research that we have conducted in this area. And then we'll look at some of the solutions, and in particular, we're probably going to focus more on the statistical process approach that we're working with, and those methods, and particularly an idea of using a cyclic histogram method that we'll cover in detail, along with some of the testing that we had conducted in our lab with some high impedance fault testing. With that, I want to talk a little bit about the OpenZ meter, and that is an open source platform that was developed by two universities in Spain, as you may know, and how we use that with our testing as part of this. So just as a basic background, Today, the voltage and current waveforms are the rawest forms of data that are analyzed for power quality system anomalies. And the main thing that we're doing with this data is engineers are observing this, and they look at information that's not provided by parameters or details, and they can tell by looking at the voltage sags. It's not just about having that actual value of the sag or the duration, but it's also in relation to the other characteristics about the waveform, whether there's other transients that may be on top of that normally would not be captured by analysis software. In this case here, we have a waveform with a voltage sag with transients along with that may be indicative of arcing that's occurring during that voltage sag. And so this having access to that waveform data is of value to the PQ engineer, not just for the event that's occurring itself, but the potential for issues that may be coming down the line, and being able to look at that data as well. So today, primarily, most PQ monitors are going to use some kind of trigger method to capture that waveform. In particular, for the most part, it's usually going to be based on the some kind of voltage setting for the RMS deviation. Typically for that, you're looking at 10% from nominal voltage, and they may also trigger on current. And typically for current, it's usually based on whatever the fault current is for that circuit. So we're not looking at a lot of details that you can find in the waveform that are subtle. And one of the things, if you are making those settings not sensitive enough, then you're going to miss those types of events, those incipient type faults, high impedance faults. But conversely, though, if we set it too sensitive, we're going to be inundated with too much data to be able to process. So it's a trade-off. And one of the things that is there's an area between that 10% setting that we're using and the nominal setting that we're currently not capturing today. We do have parameters that we're looking at that are continuous, but some of the things do not give you the detail in the actual waveform. And so we're missing some possible signatures that could lead up to more catastrophic type failures. And so there's a possibility that if we are capturing these subtle details in the waveform, we may be able to save from having a catastrophic fault. So that's what we're talking about when we say being more proactive in power quality to capture that before we get to that heavier type fault. And this is an example. This is an actual voltage waveform where we're conducting arcing experiments. And if you were looking at this waveform in a normal time series fashion, you would probably be you'd probably struggle to be able to see those deviations that are occurring at the peak of the waveform. Because we're overlaying these and playing it back in the animation, you can see some deviations that are occurring. And what's happening here is as the voltage is increasing, if we overlaid the current, you would see the current is initially making conduction and arcing through the plasma at this very point of the wave. And so it's pulling that voltage down through the impedance. So we get this very subtle notching in the waveform as that's switching on. It's almost relative to a triac or something like that that's switching on at a certain point on wave. And we'll look at more of this in a moment, but this is one of those little signatures that we're looking for, and to be able to capture some activity like this that may be leading up to a more serious fault down the road. So that's what we mean by continuous waveform. And if we used any of our PQ monitors today that has the traditional triggering methods. If we set our monitor to trigger on something like this, then we would be filling up the memory in no time, and probably wouldn't have enough memory to do continuous waveform capture with traditional monitoring. And another thing we got to look at too is, how much data can we seriously collect? And this is just a scenario here with one monitor and one site. So if just based on the samples here, if we were doing continuous waveform capture with 8 channels of voltage and current, and we're looking at 1.8 gigabytes per hour and 15 terabytes per year. And you're probably thinking, oh, well, okay, we've got storage devices that can collect up to terabytes, so it shouldn't be a problem. But if we look in retrospect to what we do today, most smart meters on average, say if a utility had 200,000 meters, they're used to collecting 100 gigabytes per year. For power quality, we have a good idea that usually it's about 100 megabytes per year, just based on some data that we've collected. So if you had 1,000 power quality meters on your circuit, you'd look at about the same, about 100 gigabytes per year. So going from 100 gigabytes per year for a large amount of meters to 15 terabytes just for one meter, it's just not realistic, right? It doesn't seem that way. So there'd be a large infrastructure change to do that. Another issue with this is the human impact, the engineer being able to observe this data. For myself, if I can look at these waveforms here scrolling across the screen, and I can tell you I can observe about 10 cycles per second. Really looking at it, I'm seeing high frequency in some of the channels. I'm seeing some low order harmonics in some of the other channels. I'm observing this and looking for any deviations. If I could do that at this speed, it would take me 48 years to look at 1 year's worth of data. So again, from a human aspect, this is not possible. So we have to look at other ways to be able to observe that data. So what are some of those solutions? Just as I showed with this waveform earlier. Well, today, what we use when we're analyzing waveforms is we aggregate this waveform up to a parameter level. So RMS voltage, for example, we may be able to look at this and see any subtle deviations that are sporadic. Flicker is certainly an algorithm that this would probably sporadically increase the flicker over time with this type of waveform. Rapid voltage change may not see as much, but you would still see some subtle change if that's calculated over time. Believe it or not, crest factor plays a role in that you're looking at the peak versus the RMS of this waveform, especially if there's arcing occurring more close to the peak. And then, of course, if you have a high pass filter and you're looking at high frequency content from a voltage waveform like this, it will show some of those things. So this is a viable solution. The only thing with all of these different waveform parameters is you lose the engineering eyeball on the actual waveform data to be able to see subtle details. These subtle details give you more information, such as the deviations occurring close to 90 degrees or between 70 and 90 degrees. Little information like that that we need to be able to capture as part of that. Another thing that we can do is kind of ride on the coattails of what's been done for years in industrial processes, and that's statistical process control. If you think about the utility compared to an industry, we make widgets. We make one cycle waveforms of voltage. So with that, if you're at 50 hertz, we're making 4,320,000 of these widgets per day. So if we had a way to be able to measure these and use the same techniques that are used in statistical process control, then we would have a way to be able to manage those deviations and triggers and have an idea of where our waveform has been, where has it deviated, and what does that look like. One of the ways we do that with trend data is we create a histogram. We look at a histogram, we can tell where our voltage RMS has been over time, how long it's been in a particular area. Well, we can do the same thing with a waveform. And that's where we're using this concept of a cyclic histogram, where you are, and I'll go over detail with this, but as you can see in here, what we have is an XY coordinates of the actual one cycle, and these are bins of this waveform that you're seeing above, stacked in, and the color shows you the amount of the waveform that have fallen into those bins. And the one thing that we can see right away is that deviation that's occurring near that 70 to 80 degree point on wave that's occurring in that waveform. So without having to observe this whole record for a period of time, you can look at this in one shot with the engineering eyeball and see that quick deviation and make some informed information from the observance. So what is the cyclic histogram? It's just as I described, tried best here with this illustration to show that. It's a three-dimensional representation of many continuous cycles that are stacked on top of each other. It is important with the cyclic histogram that the PQ phase lock looping, because the same point need to fall on the same point or degree of on that waveform for each cycle. So if it's not doing that, then there may need to be some form of interpolation or phase lock loop to correct that. But the X and Y axis is made up of the sampling of the bins, and as each of the values come in, those digital samples will fall into those bins. And the size of the bins, I might talk about this in the next slide. In this case, for the x-axis, if the waveform is 128 points per cycle, then that's going to be locked into the number of bins you have. For the vertical axis, usually we're sampling at a higher bit sampling, so there is some aggregation of putting them into smaller bins. And yes, I'll talk about it here. And so this is an example that's showing your steady state waveform. And then we had a voltage sag during this period. So that's what you're seeing with this lower piece of the sinusoidal waveform. And there was a capacitor switching transient that occurred that you can see on top of this one. And so, again, if most meters record around 16 bits, so that's scale. So there's probably some aggregation that should be performed in order to lower the amount of bins that you would have on the for the vertical portion of the histogram. And then, of course, as each bin is filled up higher, as you can see from the axis over here, you get a representation of where your waveform has been over a certain period of time. For the most part, in this case, you can see, for the most part, we had our nominal voltage for a larger period of time versus a shorter period for the sag and even shorter for the capacitor switching transient. This is kind of a representation if you go drill down to the level of each bin, and just showing this one is actual recording from 24-hour period and showing you the bin values of where this waveform has been, and showing you just an example of how many samples have fell into those bins, just looking at it up close. Now, the concept that we're deploying for this is not a continuous cyclic histogram that's capturing our traditional waveform capture. For anything that's beyond the 10% threshold setting, our triggers, we want to continue to do time series waveform capture. And every time this happens, though, what we want to do in between the events is to capture the cyclic histogram and look for those subtle deviations. And there could be days between your individual events. But what this shows you is you can continue to look at your time series events, and then you can look in between and see if there's any deviations that are occurring leading up. So that's our main use for this. Now, the one thing with the cyclic histogram is you lose some sense of timing. This arcing may have occurred at the very end or the beginning of this days between events here. And so using something like a parameter flicker, RMS voltage, or what we've created is this jolt or jerk algorithm that's basically just looking at DVDT over that period of time, and we're creating a parameter out of that to show where those deviations might occur. And in this case here, we see it's occurring at this time and space for this particular waveform. And one thing we're doing is in a lot of our research, we always need a platform to be able to deploy this and test out methods. And this OpenZ meter that was born from a collaborative project between the University of Marion and the University of Granada has been a very great source for us to test some of our ideas and research in the actual field environment. And so we have been working with this group and in applying the cyclic histogram and this jolt algorithm to this meter and doing these recordings to get some of that feedback. This is an example here that where we've put in the cyclic histogram and the jolt algorithm into the OpenZ meter. In deploying this, when we're wanting to use this in practical applications, one of the things that we wanted to do right away is look at high impedance faults. One of the issues that we have today, this is an example testing in our Linux lab in Massachusetts, where we've actually conducted some down power lines that did not pull enough current to trip relays or even trigger a recording. And these are high impedance faults, so they're not pulling a lot of current. What you're seeing in this case up here is less than 40 amps and much less in this recording here. We're in milliamps in this one recording here. However, when we look at these waveforms, we understand as engineers that there are some signatures that show this high impedance fault, and one of those is called shouldering. And what you're seeing here with this fault current is we have it's a high third harmonic content signature to where you have kind of a high crest factor. You've got the pulling in of the waveform on the sides, and it's got a high peak at the very top. And this is basically where, as the voltage is increasing, you get more conductivity at the peak of the waveform through the Earth's resistance, and it pulls more current at those peaks. And look at third harmonic and probably even use that as a trigger to do that. But there are a lot of loads out there that have the same third signature. So that probably wouldn't work very well. And so that's where we need a combination of sporadic activity, third harmonic, high frequency content that may be occurring to be able to detect some things like this. But at the same time, being able to look at the waveform as well is of value. So this is testing that we had conducted in our high voltage lab in Linux, but we wanted to reproduce the same thing and capture this with the OpenZ meter and some of our recordings that in our power quality lab. So we created our own high impedance fault small scale testing. And what you're seeing here is where we have taken a piece of wood and applied a high voltage across that and let it conduct and create arcing until it gets to the point of creating a fault and tripping a breaker. And if we look at this, the blue waveform in the middle, you can't see the details here, but you can see it in the scope at the upper right. So we see an increase in current And not until the end does it get very sporadic. This is when the plasma is actually joined here between the two conductors. And you see up here in this current that we go from more of a sinusoidal to that more triangular shape. That's that shouldering in the waveform that I was talking about. And that's one of the key signatures that we look for these arcing signatures. And if we've seen this over time, then we may be able to, before something goes into a faulted state, be able to see this signature at that point and have some kind of action that operates with that. So this is a recording. This is the actual recording, and zooming in and looking at this one portion here of that waveform. And I'll be referencing to this as we move forward and look at some of the other waveform data. I wanted to include this one just to show why there is shouldering in the waveform. Now this particular, if we're looking at the red waveform here, this is one of the shouldering waveforms. And by shouldering, meaning that it pulls in as the waveform increases, and when we get up to the top, it looks like, I guess, this could be the head of the waveform. But what is happening is, and we have high-speed capture, just zooming in on one of the arcs that are occurring here. There is some resistive conduction that is occurring here, but most of the current's going to start pulling more up here at the top of the waveform. So you can see here the arcing is just starting to be conducted here on this trail. And so the current waveform is not as prevalent until you get up to the higher peak in the voltage. And it's almost like a triac or SCR that once it's conducted, it stays conducted until you get to the zero crossing. And then once you get to the zero crossing, we have the same thing where it's not conducting as well until it gets to a higher voltage and continues with that. And sometimes you'll see this on both the upward slope and the downward slope of the waveform, and it just gets different every time you do one of these type of tests. One of the things that I wanted to be able to show is being able to use flicker or some of the other parameters to be able to see this deviation as well. And this is taking that same data that we just looked at, and you can see there using P instantaneous value, we can see that increase, of course, until it trips at this point right here. But still, it's not telling the story of looking at the waveform and being able to determine what has happened. If we take this waveform, this is the entire recording. That was a 31-second recording. That's not showing all the waveform up here, just a tiny section. This is what we get in our cyclic histogram. And so you can see before the current was on, you can see the kind of steady state while the arcing was young, and it was more sinusoidal, although we do see some deviations that are occurring. But really what we're paying attention to is this red area, which is only a few cycles represented in each one of these bends. And you can see that triangular or shouldering signature in that current waveform. And this is something that we would have missed if we were using traditional PQ monitoring trigger methods to capture this. We wouldn't have triggered on this, else we'd been inundated with too much data. And this could represent more than just 31 seconds. This could represent a whole day or any other time span in between traditional triggers. And this is a representation of the voltage. The one thing that we learned right away in conducting this research is the cyclic histogram, looking at a full 60 hertz waveform, is kind of wasted because you have only a few bends that are exposed to any kind of deviations, especially if we're only talking about subtle deviations in the waveform. So in this case here, we want to be able to spread those bends out and look at more deviation. And one of the main ways to do that is just filter out the 60 hertz component and look at the higher frequency deviations or anything above 60 hertz to do that. So one of the things that we did was remove, we first started just removing the ideal 60 hertz component in our case. And what we were left with is this blue trace that you're seeing down at the bottom. And this is basically just showing us the harmonics that are left over. Not a lot of deviations that can be depicted, at least looking at it this way. However, if we go back up here and we subtract the first cycle from the remaining cycles, so we're basically taking what I call the nominal voltage, which is that first cycle, and subtracting it from the rest, what you get is this red trace down here. So this first one, of course, it's going to be 0 because we're subtracting it from itself. But then you get to see how is this deviating as the cyclic histogram is created. And if we take this and put it into the cyclic histogram, well, before we get to that, actually, this is what one wave shape looks like. So here is that nominal voltage, the dark blue, and the light blue is the voltage during that fault, right close towards the end. And I'm showing the current here on the left that shows some of that minor shouldering that's occurring. Well, if you take that first cycle and subtract it from that fault cycle, what you get is this voltage difference over here. And because you are going through that impedance, that fault current is traveling through that impedance and it pulls the voltage down, you get a voltage drop. This is basically that drop across that impedance. And you get that same signature of shouldering with that waveform. So now we want to talk about doing this. We want to take and put this voltage difference into the cyclic histogram. This is also another aspect. When we first switched on the circuit to do this arcing, this is transformer inrush from closing into that circuit. Same thing. We subtracted that portion of the circuit from the voltage from the nominal, and sure enough, you get the same signature in the voltage difference. So this is the cyclic histogram and what it looks like, the voltage. Now we've got a lot more variability that we can see. We can see more details than looking at the voltage with the 60 hertz and nominal component. And so what you're seeing here is, for the most part, in the very beginning, is flat. And as we moved into the arcing, you start seeing some deviation from the nominal waveform. You start to see more of the shouldering in the red region here that's occurring, and see some of those signatures. So what you're looking at here is the voltage difference over time from that nominal voltage. And I realize that we're running close on time, so I'm going to speed up a little bit here. So again, that's showing the shouldering. And I think this is the last slide here. This is looking at the same event, just to give you an idea of how the cyclic histogram can be applied towards statistical process control. So, and doing this so you can create triggers for waveforms, because right now what we tend to do is just we rely on a 10% threshold, and we don't try to make that any tighter because we're afraid that we're going to trigger more recordings. So it requires you to sit down with what you're going to trigger against and make some adjustments and get that feedback. But what can be done here, if you did collect this data, if you treated it like statistical process control, if we looked at this first part here under A, this is during the nominal voltage. If we were going to set some plus or minus 3 sigma limits for this, our limits would be around 1.2% of the wave shape deviation. So I'd be very tight. This is looking at the voltage difference down here. So we would have 2 volts deviation, and that could be our limits. But if we're going to record longer, and if we got into this, say, this first section here where we're adding the transformer load, we see that deviation has grown a little bit. So we would want to maybe set our limits to 2.7%. And if we go a step further and include this whole recording of the incipient fault, then our plus and minus 3 segment limits would be 6% based on that wave shape deviation, or 10 volts. So this could be, kind of a worst case, and maybe you would, with this, you would set your triggering limits to 5% and be able to trigger on that. So with that, I think I've used up most of the time. And is there any questions with what we discussed today?
Thank you very much for your presentation. Questions, please? Yes, from the audience, from the on-site audience. Please. Name and affiliation, please.
Yes. Hi, Bill and Tom. I'm Francisco Gil Montoya. I'm Paco from the University of Almeria.
Yes, sir. Yes, sir.
First of all, I would like to congratulate you for your presentation. It was very enlightening and informative. On the other hand, I would like to publicly thank EPRI for your support to the OpenSea Meter project during all this time, and for your trust and patience you have shown repeatedly. We are proud that such a prestigious institute makes use of our technology, this technology that we have developed here in Almeria, and that it serves to improve the PQ detection system you are working on. I have a few questions to ask you. For example, I see that your development is mainly focused on voltage waveforms individually. I find this new way of looking at the data very, very interesting. But maybe there could be a way to generalize it to multi-phase systems as a whole. How you thought about it?
Yes, I definitely agree. This is something that we're looking at right now, just treating it as a single phase. But we do want to find ways to be able to deploy this into 3-phase analysis. And I appreciate working with you guys. You guys have created a great system and have great ideas in how to look at different waveforms, just in my work with you so far. And I think there are some other ways that we can be looking beyond just what's the cyclic histogram, and even looking at analysis of 3-phase waveforms in different formats, so maybe even a 3D cyclic histogram with combined waveforms. And I think we've talked about some of this in the past and some of those methods.
Okay. Regarding the use of the OpenSea meter system, I'd like to ask you that what was the main reason to I open double quotes, to risk using this new system? What are the main benefits you found here that were not in other monitors, for example?
Honestly, it is the open source interface. It is, and the fact that it has a lot of the infrastructure built into it that is working great with what you've created. So for EPRI, what we've struggled with in the past is we have these ideas and we put them down on paper, but it's the most of the research is when we actually apply it and take it into the field. So in the past, we've had to work with monitoring manufacturers that are more closed source, that are proprietary type of developments. And so, it was more of a struggle to be able to work with those manufacturers than what we're finding with this OpenZ meter. The OpenZ meter just creates this environment, just like any open source software. For our scientific institution, we collaborate better with open source.
Okay, thank you. So I have a final suggestion. I wonder if you could stretch the wave and convert it to a straight line. This would allow a better visualization, I think, with a better vertical resolution. It is somehow similar to remove the nominal voltage, something like a linear transformation, maybe. What do you think about this?
Oh, I think anything is on the table. This is just, some preliminary ideas to be able to look at the voltage in a different way. It's just a matter of being able to translate that. So I think there's this whole concept of continuous waveform analysis. And hopefully I've got this point across today is we have to look at more compact aggregated ways to look at this, but still get the information of where that waveform has been. And I think that's the biggest struggle right now in tracking incipient faults is you got to have the data. And we can't even do AI learning,
Yeah.
machine learning, without having this data. The data, it's not going to magically appear. And that's the only way that we can move forward and use AI for incipient fault detection in the future is we got to create the data. So we got to get past that first step.
Okay, so thank you again. Thank you very much for your nice presentation, and also thank you for your presence here. So thank you.
Thank you, Francisco. Thanks for inviting me.
Too. Other questions, please? Also, if there are questions from the audience online. Anyone else? Okay, I want also to thank you for your presentation.
I have a question.
Sorry, I haven't seen.
Yeah, from the audience in the room.
It is dark here.
Yes, it is.
Sorry, please, sir.
Okay, well, first, thank you for the presentation. It was really interesting. I love the use of open source hard and software in this case. My first question is really brief. What time resolution are you using? Because you are taking samples of, it seems at a very high sampling rate.
Yes. With the OpenZ meter, we're looking at 400 samples per cycle. And some of the other recordings that you're seeing in here is anywhere between 128 points per cycle to 1,024 points per cycle.
Oh, okay, thank you. And have you had any issues with, with frequency deviation because you are basically adding values at fixed points in time, I guess. So if the frequency deviates slightly from the nominal value, have you had any issues with that?
Absolutely, and that's very observant of you to notice that. It's definitely an issue. Our 60 hertz is never 60 hertz. It's always deviating plus or minus. And so that's part of what I was talking about at the beginning with the phase lock looping. As you're collecting the waveform data, in order for each sample to align on the specific phase angle on the waveform itself, is you have to conduct phase lock looping, which requires you to do continuous frequency sampling in order to align that. And one way to deal with that is having the meter do phase lock looping, or you have to do some kind of post-analysis where you interpolate those points and then make sure those line up.
Okay, thank you very much.
Thank you, too. So, another question, please.
Thank you. My name is Peter Kadar from Hungary. Congratulations for the presentation. So my question about the future. So as we know, in the power system, there are the category of the secondary devices, the protection. The protection must be there. It must continuously check the situation and very robustly, rarely operate. It is another approach. It is the continuous, very detailed analysis. Where is the border between this analytics and between the protection devices? Maybe in the future, all the protection device will continuously analysis made, or it is a two different things. Thanks.
Well, I would never say it is a completely two different things. Certainly, we're a long ways from that. And you do have to have a lot of trust in your algorithms inside your protection system in order to operate. I think there's going to be a lot more learning that's done from this. Like I said, we haven't been collecting this data. We haven't been looking at it for a long time. So it's going to take a while to understand it. And then, statistically over time, as we see whether it's of value to be able to be trusted in our protection system.
Okay, thank you.
Okay, if there are any questions, the audience online, not. However, our time is up, and I have time only for congratulating you, Tom, for your nice presentation and for your novelty of this presentation. Thank you very much, and we hope we'll meet again, perhaps face in face, in the next conferences of IQFQ. Thank you very much. Thank you very much at the audience online, at the audience on site, and prepare for the next session of our conference. Thank you very much.
Thanks for having me.